All right, today we're going to kind of do some extensions of what we did last time. We're going to prove the Lineal Mansour Nisan Theorems from 1989 about constant depth circuits, which is cool. This is kind of like the second awesome result about theoretical computer science using Fourier analysis. It came right after the Concali lineal one from 1988. And we're also going to prove this Mansour theorem about DNFs that we mentioned last time that almost proves the Mansour conjecture. And in both cases, the technique is going to be using random restrictions. We saw last time that if you do the random restriction of a Boolean function, it's very easy to get formulas for its Fourier coefficients. And as we'll see today, random restrictions really act severely on DNFs and constant depth circuits. So that will help us make the connection. OK, so you remember last time we talked about DNFs and CNFs. So DNF, remember, looks like you got an OR gate, and then a bunch of AND gates. And then they fan out to the variables and the literals. So you can imagine writing x1 and x1 bar down here through xn and xn bar. OK, that's a DNF. If you interchange ORs and ANDs, it's called a CNF. And yeah, today we'll talk about the generalization to constant depth circuits, which, as you may guess, is just now you have more layers of ANDs and ORs. So you might have multiple ORs up here, also fanning into AND gates, which go down to the variables. And then you have ANDs up here. OK, this would be an example of a depth 3 circuit. And of course, you can go to like a depth 4 circuit, which may have a bunch of depth 3 circuits underneath an overarching OR. OK, and it can start or end with an AND, and it can start or end with an OR at the bottom. The only importance is that it alternates. And that's essentially without loss in generality. If you have like two consecutive AND gates, you can just like merge them together. So in fact, any depth D circuit can be put into this sort of layered format at the expense of like factor 2 times D in size or something. And we're going to think of D, the depth, as like a constant. So this is the only kind of circuits we'll talk about, possibly in this class. OK, so this generalizes CNF and DNF. This is a higher depth version. So this row here is called layer 1 of gates. This is layer 2. OK, and in general, it goes up to layer D. And that's called the depth. So CNFs and DNFs are depth 2. And we also have the parameters size and width. So size of a general depth D circuit is equal to the number of gates, as they're called in circuit complexity, at layers 1 up to D minus 1. OK, so we don't count the one gate that's at the very top. It's not a big deal. You can count it or not count it. We don't care about addition of 1. But this is just for consistency with the definition of size for like DNFs, where we just counted the number of ANDs. OK, and there's also, we're going to eventually need like a notion of width for such a circuit. This is kind of a bit technical and not that important, but it's the maximum. It generalizes width for CNFs and DNFs. It's the maximum fan-in at layer 1. OK, so it's you just look at all the things that are closest to the variables and look at their maximum fan-in. OK, so this is a pretty interesting class of circuits. Polynomial-sized circuits of this form are called the complexity class AC0, if you know about computational complexity. And they're kind of getting towards the limit of what we can really understand and prove lower bounds for. OK, so today's final goal will be this theorem of LMN, Lineal Mansour and Nisan from '89. And it's just about the Fourier concentration of functions computable by small constant depth circuits. So it says size S, depth D circuits have their Fourier spectrum epsilon concentrated up to degree, let's see, O of log s over epsilon to the d minus 1 times log 1 over epsilon. Okay, so to parse this, first imagine that epsilon is constant, so it's just like log of the size to the power of d minus 1. Okay, which matches what we saw last time for depth 2, CNFs and DNFs, that was just degree log s. Okay, and this is pretty great because for polynomial size circuits, that's when s is like poly n, this is like log n. So the overall statement is that almost all of the Fourier spectrum of any function computed by a constant depth circuit only is below degrees polylog n. Okay, thinking of d as a constant. And also, as a bonus, the dependence on epsilon is quite good. It's like logarithmic. Actually, since I have it up here, I cannot help but point out that this was very, very slightly sharpened by Hostad in 01. He got O log s over epsilon to the d minus 2. That looks good. But log s log 1 over epsilon. Right. So you still have like d minus 1 powers of log 1 over epsilon and also d minus 1 powers of log s, but it's like slightly better if, I think if epsilon is really small compared to 1 over s or something. I don't know. I wanted to point that out since this is not the best thing known. But if you think about epsilon as constant, for example, it's the same.
What's the lower bound?
It's of this flavor if epsilon is comparable to 1 over s. It's something similar to this, but like so for example, if d is 2, this is log s times log 1 over epsilon. And I think the lower bound is like log s plus log 1 over epsilon for d equals 2. So it's pretty close, but not exactly known to match the upper bound.
And for larger d, we do not know.
It's similar in that like the right dependence on log s is like to the power of d minus 1, but the exact interaction with epsilon, which can be relevant sometimes for like pseudorandom generators and stuff, I don't exactly know. Okay. So yeah, so this is a great result. It has some corollaries, both positive and negative. One is, as we have seen many times before, if you have like a concentration result like this, you get a learning result. And LMN were actually the people that introduced this low-degree learning algorithm, and that was one of the main corollaries in their paper. That's probably what Mansour was thinking about, at least. So, I mean, poly n size, depth d circuits. Let me just try to maximize all parameters. Are learnable from random examples only to any error like epsilon equals 1 over poly n, which is quite great, in time n to the O of log n to the d. Okay, basically n to the concentration bound. So that's pretty good. I mean, it says that this class AC0, I mean, the colloquial way to phrase it is that this class AC0 is learnable from random examples only in quasi-polynomial time, which is quite nice. There's also a very nice negative consequence of this theorem. So this says that if you have an AC0 circuit, like almost all of its Fourier spectrum is below polylog degree. In particular, that means it can have very little Fourier, very small Fourier coefficient on the largest Fourier coefficient. And that measures its correlation with the parity function. So another corollary is this. Let's just fix any positive epsilon 0. And let C be a depth d circuit. And suppose that C is like slightly good at computing the parity function. So say that the probability over random x that C of x equals the parity of all n bits. It doesn't even have to get it right, but say it's just like slightly better than guessing. a half plus epsilon 0. So it gets it right on just even 51% of the inputs. Then it has to be a very large circuit. Then the size of the circuit is at least 2 to the omega n to the 1 over d minus 1. Okay, so if you fix, okay, I don't know, depth 3, for example, it says any depth 3 circuit that's even, computes parity correctly on 51% of inputs has to have size at least 2 to the root n. It goes into this thing. I'll prove this in a second so you can read it out. This is actually not the, okay, if you really care about all these parameters, this does not give you the best known trade-off in terms of epsilon naught. But it is sharp in terms of the degree. For example, there is a circuit of depth d of size 2 to the order n to the 1 over d minus 1 that computes parity exactly. Okay, so this is actually quite sharp as a lower bound. Okay, and this is like a stronger statement than the well-known statement that you cannot compute the parity function in the circuit class AC0, constant depth circuits, of polynomial size. And I'll write a proof of this, which will implicitly give this dependence on epsilon. It's just the same that this hypothesis is the same as saying that the correlation with parity is at least 2 epsilon naught. So that the degree n Fourier coefficient is at least 2 epsilon naught. But we know that, all but, I don't know, 1 minus epsilon naught of your Fourier spectrum is below degree, like log s to the d minus 1. So the Element Theorem implies, if you take the epsilon in it to be smaller than this epsilon naught, that this degree bound, O of log s over epsilon naught, well, let me just turn all the epsilons into constants, had better be at least n, the degree of this Fourier coefficient. Okay, and then just inverting that gives you s is greater than or equal to 2 to the omega n to the 1 over d minus 1. Okay, so this will be our ultimate goal for the day, to prove this concentration result. But we'll spend some time just working on DNFs and CNFs. And we'll get some powerful results about their Fourier concentration as well. Any questions so far? Okay, so the way we'll get these results is by making a very powerful statement on the combinatorial side about what happens when you hit a DNF with a random restriction. So let me start writing a theorem over here. So let's say we have, let's let f be a Boolean function which is computable by width w DNF. And let's imagine a random restriction, JZ, be a delta random restriction. And think of delta as being less than or equal to, maybe even in your head a lot less than or equal to 1 over w. Okay, so remember delta is like, when you're going through the coordinates, the probability that that coordinate stays free, unfixed. Okay, and each term has like w coordinates, or up to w variables in it, or literals. So for example, because of this, we know that the expected number of free variables in a given term is at most 1. Okay, and if you think of delta as a lot smaller than 1 over w, it's like a lot less than 1. Okay, so we're in the regime where when you do the random restriction, for each term, the expected number of free variables is actually less than 1. Like, it's probably most likely you'll fix all of the variables. Okay, now there's like a huge number of terms, so it's not going to be the case that you always fix all of the variables in them. But what are the things that could happen? So the most likely thing that will happen is that you'll fix all of the variables. And a term in a DF is an AND, right? So, I mean, each variable you fix gets fixed either true or false with equal probability. So probably one of the things that you'll fix will get fixed to false. And like that term will just become false. And if you imagine the overall DNF, it's as though you just deleted it. So that's for each term, like that's overwhelmingly the most likely thing that will happen. But let's not even think about like the somewhat unlikely things that could happen. So actually, like the next most likely thing to happen, although it's still very unlikely, is that all of the terms get fixed to true. Sorry, all the literals in the term get fixed to true. Okay, that's only going to happen with probability like 2 to the minus w, if it's a width w term. But it could happen. But actually, even if that happens, your DNF still simplifies quite nicely. In that case, it's like you fix the term to be true. So actually, the whole DNF overall just becomes true because, well, on top you have an OR. And you fixed one of its inputs to true. OK, so you're quite happy. Like in the most likely case, you're pretty happy. In like the next most likely case, you're actually extremely happy. Your DNF becomes constant. The only thing that's left is like the freakishly unlikely case that like not all the variables get fixed. So there's at least one free variable, even though the expected number was very small. And all the things that did get fixed got fixed to true. That's the only case in which like nothing much happened. So in that case, like let's say most of the variables got fixed to true, and a few of them remained unfixed. So this AND survives as just like a smaller AND. So that could happen, but as I said, that's extremely, extremely unlikely. So all of which is to say that it seems in this regime, when like delta is a lot smaller than 1 over w, there's like an excellent chance that your DNF will get somehow completely killed. And in fact, on your homework, you're asked to show that the probability over the random restriction that the restricted function is not a constant is at most 5 delta w. Actually, even 3 delta w, I think, is on your homework. Okay, which is, you know, it's pretty small if delta is a lot smaller than 1 over w. So that's actually a pretty good statement, but it's not even the most powerful statement that we'll use. This is kind of the baby version of the real statement. And the ultimate statement along these lines is due to Hostad. It's called Hostad's switching lemma, for a reason we'll eventually see. This was proved by Johann Hostad in '87. It was his PhD thesis. It says, for all k, a natural number, the probability that the restricted function cannot be computed by a shallow decision tree is really small. So let me write this. Okay, by this notation, I mean you look at the restricted function and you look at the least depth of a decision tree that can compute that function. So for your favorite number, like, I don't know, 4, the probability that the restricted function cannot be computed by a depth 4 decision tree is like delta w to the 4th times a constant. Okay, so you can ratchet up k bigger and bigger, and like the left-hand side gets like, you know, sort of exponentially, it goes down exponentially.
Computed exactly.
Pardon me? Yeah, computed exactly. Yeah. So if you took k to be 1, you would get back the baby version that's on the homework. Because if you take k to be 1, this is 5 delta w. And this is like, what's the probability that the restriction function needs depth 1 to be computed as a decision tree? The only functions which can be computed but do not need depth 1 are constant functions, the ones that are just, there's a leaf right at the root. Okay, in particular, like a function that's computed by a depth k decision tree can only depend on like 2 to the k variables. So it's a very powerful statement. Any questions about the statement of this? Okay, so we will not prove this statement. It's a problem in probability or combinatorics, and it's a bit involved. It takes like a few pages of writing. So it'll take us the rest of the class. So we're just going to take this as a given, and you can do the k equals 1 case on your homework. Okay, so let's now pretend that we know this fact. So how are we going to connect it to the Fourier side? The key observation that we'll make is that, this says that it's exponentially unlikely that you won't become like a depth k decision tree, depth k minus 1 decision tree. The key observation that we'll make is that a function that has a depth k decision tree has degree at most k. I hope you remember that fact from a while ago. If you just take a decision tree of depth k and like do the Fourier interpolation, you'll just see that you get something that's degree k. So we know that if f, let's say if the decision tree depth of f is at most k, then the degree of f is at most k. Okay, or in other words, the Fourier weight above degree k is 0. Okay, so if your decision tree depth is like less than k, you have like the ultimate Fourier concentration up to degree k minus 1. Okay, so actually we're now just going to put those two facts together and calculate. So let me do that over here. This is going to be a somewhat calculation-intensive class, in fact. Okay, so here's a slightly technical-looking lemma that we're going to use twice. So let me call it lemma star. Okay, this is just about a generic function. It has nothing to do with DNFs or the switching lemma. So let f be a Boolean function. And let J, Z be a delta random restriction. And let epsilon be the probability under this random restriction that the decision tree, if I just write dt of a function, that means the least depth of a decision tree that computes it, is at least k. Okay, I should also add let k be a natural number. Okay, so imagine these parameters are small, so like it's very unlikely that f does not shrink to a function whose decision tree complexity is less than k. Then f is Fourier concentrated. Then f is 3 epsilon concentrated up to degree 3 k over delta. Okay, so if you can find a delta which is not that small, such that the associated epsilon is small, this gives you a very good Fourier concentration statement. Okay. All right, so to prove this, suppose you do a restriction, and the Fourier tree, the decision tree complexity is less than k. Then by this observation, we know that the weight above level k of the restricted function is 0. Okay, because it has degree strictly less than k. On the other hand, there's some chance that you do the restriction and the resulting function does need a decision tree of depth at least k. In that case, we'll just use the most trivial bound, which is that perhaps the weight above level k is 1. But this thing only happens with probability epsilon by hypothesis. Okay, so what we know is that the expected value over j and z of the weight above level k, which I'll just write out more explicitly, sum over S of cardinality at least k of the restricted guy's Fourier weights, f hat s squared. We know that that's at most epsilon. Okay, so let's go ahead and blindly exchange this sum and the expectation. So this is the sum over all S of cardinality at least k of the expected value over j and z of f j z hat s squared. And this is the expected square of the S Fourier coefficient of the restricted function. So I know you guys all remember the formula for that. Misha? I think what you're going to say, Misha, is that it's this. It's the, okay, let's leave the sum over S at least k. This is like the sum over all u of f hat u squared times the probability that u, this is over j, u intersect j equals S. It's kind of like you have all the coefficients, right? And then when you're doing the random restriction, like some of them get fixed, and the ones in j remain free. So like you're kind of wondering, like, what's the chance that for this original set u, that the set of guys in u that remain free is exactly the set S that I'm interested in? And yeah, the formula just works out to be this. Okay, well anyway, we did that last time. Take my word for it. So now we have to interchange these two sums. So that's sum over all u f hat u squared times the probability of what? Who's very good at interchanging sums?
Probability intersections S at least k.
Yeah, that's right. It's the probability that the intersection has size at least k. Okay, the way to see that is you should just sum over all S and stick times 1, the indicator that S is cardinality at least k here. That's the same thing. And then once you have like unconstrained sums, it's easy to switch them, and then you can push the indicator into here. Well, anyway, that's an analysis trick. If you think about it for 2 seconds, this is what you get if you interchange the sum. Okay, great. So we're almost done. We just need to calculate a little bit. What's going on here, in fact? You see, this is a random variable. Fix u. The probability is over this choice of j. This is the free coordinates in your random restriction. So you're looking over all the things in u intersect j. The cardinality of that is a random variable. What is its distribution? Yeah, that's right. It's binomial. It's like you have cardinality of u trials with like parameter delta. Right? This is binomial cardinality of u delta, because you go through each of the u elements in u, and with probability delta, it stays alive and goes into j. Okay, so in particular, right. So in particular, okay. Good. So let me make the following observation. When U is a set whose cardinality is at least 3k over delta, that's kind of what we're ultimately interested in. We know that the expected value over j of the cardinality of u intersect j, well, it's binomial parameter delta in this number of trials, at least, so it's at least 3k. Okay, and it's binomial, so its mean is like 3k, and you're kind of curious about what's the probability it'll be at least k. This is like factor 3 lower than its mean. That's a very unlikely event. So you can use Chernoff to bound it. I won't bore you with the full explicit calculations, but by Chernoff, that's very unlikely. The probability that u intersect j is less than k is at most, if I did my Chernoff right, it's like at most e to the minus 2/3 k, something exponentially small in k. And we don't even really need to get stressed, because I'm just going to say this is at most 2/3. It's a very, very, very weak bound. It's actually exponentially small. Whatever, it's at most 2/3. You see that that is only going to go into this factor here, so it's not a big deal. OK, so this star, that means this probability is at least 1/3. OK, it's actually practically 1, but it's at least 1/3. So star is at least, I'm just going to drop all the terms when cardinality of u is small. I'm just going to give them away. But for the remaining terms, I know that this is like exponentially close to 1. I'm going to use this pathetic bound that it's at least 1/3. And I think I actually get to draw the little box here, because eventually we have this thing is less than or equal to epsilon. So I multiply by 3 on both sides, and I get the exact statement. The weight above this degree is at most 3 epsilon. OK, so it's like a calculation. OK, and intuitively what happened was like, if f under random restriction is very likely to become like a really low degree function, then it can't have tons of Fourier weight up high, because, I don't know, all that Fourier weight has to totally go down below level k with high probability. OK, great. So once you have these two things together, you can just plug them into one another and get a Fourier concentration result for width w DNFs, which is noticeably better in one aspect than the one we got last time. So literally putting the parameters together, if f is a width w DNF, yeah, its spectrum is epsilon concentrated up to degree O of w log 1 over epsilon. OK, and last time, the only bound we got was w over epsilon. And that was because we observed that with w DNFs have total influence at most 2w. So by this little Markov thing, for epsilon concentrated up to 2w over epsilon, this gives an exponential improvement in epsilon. And the proof of that is just, I think you should take delta just to be a little bit less than 1 over the width, so 1 over 10 times the width. And so you see, when you do that, this thing becomes a half. So you get probability that the random restriction needs decision tree depth k is like 2 to the minus k. So then you just take k to be some big constant times log epsilon, log 1 over epsilon. OK, so the 2 to the minus k becomes epsilon, and this degree bound 3k over delta becomes like log 1 over epsilon times w. OK, so that's pleasant. All right, so in fact, we can squeeze a little bit more out of this exact same proof strategy. for this proof, we use the fact that a decision tree of depth k has degree k and is thus totally concentrated below degree k. Another thing that we proved a little while ago, it's also simple, is that if f is a function computable by a decision tree of depth at most k, then its Fourier L1 norm, which you remember from the homework we wrote like this, is at most 2 to the k. So this is some kind of measure also of like the sparsity of its Fourier transform. It's like, if you add up all the Fourier coefficients, it's not that big. Okay, if you remember how we did this last technical thing, we did a random restriction and said if you become decision tree depth less than k, you're concentrated below level k. If we instead use this fact, you get, maybe I'll leave this, should I do it or should I make it an exercise? Let me just do it. So let's see. So let's look at the expected value over a random restriction, delta random restriction, of the Fourier L1 norm of the restricted function. So by this fact, this is less than or equal to the expected value of 2 to the decision tree depth of f, j, z. Okay, because this is always a bound on the Fourier L1 norm. Okay, but on the other hand, just by definition, this is equal to the expectation over j and z, the sum over u, f restricted function hat u. Okay, so I'm going to exchange the sum and the expectation, and then I'm going to take the absolute value out, which is OK by triangle inequality. So I get sum over u, absolute value of the expected value of j and z, of f hat j z u. Okay, and now remember, even easier from last time, we also had a formula for the expected non-squared Fourier coefficient of a function under random restriction, and it's just delta to the cardinality of that thing. Okay? Great. So let's still imagine that f is a width w dnf. Okay. So then this expectation is going to be at most the sum over all d going from 0 to infinity of 2 to the d times the probability that the decision tree complexity of the restricted function is d. Okay, and Hostad tells us that's at most 5 delta w to the d. 5 delta w to the d. That's by the switching lemma. Okay, so now this is going to be exponentially small. I still have to crush this 2 to the d, but that's OK. So let me take delta to be like 1 over 20 times the width. OK, so this is sum d equals 0 to infinity, 2 to the d times 1 over 4 to the d, which is 2. It's the sum of 2 to the minus d. So let me reorganize everything I just wrote there. It's probably our most painful calculation of the day. So what we've eventually shown here is that, OK, this is the dividing line. this stuff is all less than this. I shouldn't have done it like this. This is like a horrible board technique. Yes. So we got this is less than or equal to 2, and delta is this. So what we got is that sum over all u of 1 over 20w to the cardinality of u, f hat u, is at most 2. Okay. And I'm just going to drop some of these terms. I'm only going to sum this over u's that are at most k. So then this thing will always be greater than or equal to 1 over 20w to the k, f hat u. Okay, so it implies this sum over u less than or equal to k, f hat u is at most 2, 20w to the k. Okay, sorry about all the calculations. We're kind of almost done. What this is saying is that if you're a width w DNF, then it's kind of like the decision tree statement. It's kind of trying to say that at least at low degrees, the Fourier concentration, or the Fourier spectrum is pretty sparse. The sum of the Fourier coefficients in absolute value is at most something to the k. And once we have this, we're going to actually be able to prove, so let's erase this monstrosity. I really want to keep this up for later. We're going to be able to prove this theorem of Mansour that says with WDNFs have almost all their Fourier spectrum concentrated on w to the w many coefficients. Remember last time we saw that like n to the w is trivial. Mansour conjecture 2 to the w, and I asked you what's between 2 to the w and n to the w. And it was w to the w. That's what we're going to show just now. OK, and it's going to be a few more calculations. So we managed to get this using switching lemma. OK, so now I'm going to actually take k to be a fixed value. Some big constant times w times log 1 over epsilon. Okay? We kind of know that the Fourier spectrum is concentrated up to this level. That was the corollary I just erased. So the corollary I just erased said exactly that the sum over s bigger than this k of f hat s squared is at most epsilon. Remember, we showed that for a width WDNF, almost all of the Fourier spectrum, all but epsilon, is below this degree. And let's also write down this fact. If you look at the guys below this degree, let's say greater than, sort of the Fourier L1 is not that big. Let me just write it's O of w to the w, let's say w, the O of w log 1 over epsilon. Okay, I just plugged k equals what it is into here. So if you've already finished your homework, which would be awesome, somebody did, yeah. You remember that one of the propositions that you're asked to prove is that if a function has small Fourier L1 norm, then it's concentrated on about that many Fourier coefficients, something like the square of that many. Okay, and I'm actually going to just do that. I was like, I may as well do it. So what I'm writing here will essentially solve one of your homework problems. So I was looking for a way to make sure you paid attention to this most calculation-intensive bit. OK, great. Let me call this L. I hear all this rustling of paper. It's great. OK, so now I'll just tell you, what I'm showing here is that with W, DNF is concentrated, its Fourier spectrum is concentrated on a small number of coefficients. So I'll tell you which they are. Let F be the set of all coefficients U, such that A, U is low degree, and such that the Fourier coefficient is big. at least epsilon over L. Okay, we know that most of the mass is down low. So just like, let's take all the guys that are down low and big. Can somebody tell me a bound on the cardinality of F? An upper bound. No points for a lower bound. I think you were going for n to the k, but it's better than that. Very close. L squared over epsilon, that's right. Because every coefficient that's in this script f is at least epsilon over L, and it's low degree. And number 2 says if you sum up all the low degree guys, you get at most L. So you have some things summing up to L. All of the things are at least epsilon over L. They're at most L squared over epsilon things. Okay, that's by 2. Good. So, and this is, of course, I mean, the squaring and the 1 over epsilon are kind of irrelevant to this. So, I mean, this is also W O of W log 1 over epsilon. So the last thing I need to show, and I hopefully can do it in this much space, is that indeed F is epsilon concentrated on this collection of coefficients. Okay, and that will prove Mansour's theorem. Sum over U not in script F of F hat U squared is at most order epsilon.
Can you lose the factor of 1 over epsilon, or you chose to ignore it?
I mean, it's really this over epsilon.
Yeah.
But that's like, I could write over epsilon as times 2 to the log 1 over epsilon. And since I already have W to the log 1 over epsilon, that doesn't, it can all go into this O. But yeah. So this is Mansour's theorem once I prove it. And remember, the most typical case, for learning theory is when you're looking at poly-size DNF, which means the width is like log n. So this is like log n to the log n, which is like n to the log n, like tantalizingly close to polynomial. OK, so the proof of this is, this is at most the sum over U bigger than k of F hat U squared. That's at most epsilon by 1, plus the sum over U less than k. If you're cardinality less than k, but you're not in script F, it has to be because you're small. So this is like, therefore, F hat U is at most epsilon over L of F hat U squared. OK, but I can write this as like absolute value of F hat U times absolute value of F hat U. Yeah, this is what you should be writing down. And this first F hat U is at most epsilon over L, so I can put epsilon over L here. And then it's like I'm summing up, I mean, this is like epsilon over L times the sum sum over U less than or equal to k of F hat U. And this is L by 2. OK, so I get L times epsilon over L, which is epsilon. OK, enough of that mess. Any questions? OK, so at high level, this what we ultimately cared about was sort of trying to say that F had a fairly sparse Fourier spectrum. And this Fourier L1 norm, the sum of the absolute values of the Fourier coefficients, is kind of a good analytic proxy for the sparsity. Certainly, the Fourier L1 norm is at most the sparsity, but they're kind of related. So since we knew something good about the sparsity of decision trees, we were able to combine it with this powerful switching lemma and get something about the sparsity of DNFs. OK, so great. Plenty of time left to do our main goal for the class, which is the Element Theorem that says constant depth circuits have most of their Fourier spectrum concentrated at low levels. And this lemma star is a great lemma for telling us that a class of functions has good Fourier concentration. All we need to show then is that if you're a constant depth circuit and you hit it with a random restriction, there's an excellent chance that it becomes a shallow decision tree, expressible with a shallow decision tree. And then we can apply this lemma. So in fact, that's exactly what we'll show. We'll show a theorem that has no Fourier content. Sometimes you got to do it, though. Let f be a function which is computable by a size s, depth d, and I'll even throw in width w circuit. And set delta to be the following outstanding number: 1 over 10w times 1 over 10l. I'll say what that is. So the d minus 2, l being log s over epsilon, 2s over epsilon. All will be explained. Now, if you take a delta random restriction, it's very likely that f will become a shallow decision tree. The probability that f, j, z needs decision tree depth log 2 over epsilon is at most epsilon. OK, so this is a theorem, a combinatorial theorem, saying that if you take a constant depth circuit, hit it with a sufficiently strong random restriction, it's very unlikely that the restricted function will need a deep decision tree. OK, and once we prove this theorem, which is the last thing we'll do, you can plug it directly into this lemma and get essentially the desired Fourier concentration result. It's kind of awesome they did this back in 1989. Yeah, so the Element Theorem is basically a corollary. We just get straight up that such f are, I don't know, 3 epsilon concentrated up to degree. What do we need? We need like 3 times this is the k times the reciprocal of this. So let me just start dropping the constants. It's like O. We're going to get a w. And then we're going to get log s over epsilon to the d minus 2. And then we're also, this is the k, so we're going to get log 1 over whatever, epsilon. Which was basically LMN. LMN was the same thing, except instead of w, it didn't have a w. It had another factor of log s over epsilon. Remember, it had log s over epsilon to the d minus 1. Can somebody tell me how to get the final version of LMN, given this version? So I just give you like a depth D size S circuit, but I don't promise anything about its width. How can you like use this fact? Yeah, that's right. It's the same trick we use like for DNFs, like dropping the really long terms, and also decision trees, just like chopping off the really long paths. I don't know if you remember, but like the definition of the width of a circuit was like the maximum fan-in at the layer 1, the bottom layer. Okay, so if you have a size S circuit, just delete all of the gates at layer 1 that are wider than this. Okay, what you get is a new size at most S circuit with this width. And what I claim is that like you've hardly changed the action of the circuit. It's just because terms at the bottom of width longer than this are only like made true or made non-trivial with probability epsilon over S. So if you union bound, you can union bound over all at most S such gates. You only change the circuit on an epsilon fraction of inputs. So once you truncate this, you get a function. People buy a small width circuit that's epsilon close to the original thing. So maybe you lose another epsilon in the concentration, but there are big O's everywhere. OK. So what I'm therefore saying is it remains for us to prove this combinatorial statement. Any questions? OK, great. I can finally erase this board now. OK, so let me redraw the picture. Actually, before I redraw the picture, this is what we need to prove. What will we do if D equals 2? OK, if D is 2, it's just either a CNF or a DNF. I'll give you a hint. This can also be or DNF, CNF. What I'm saying is if D is 2, what do we need to prove? We need to prove that if this whole piece goes away, delta is just 1 over 10W. So we need to prove that if you do a 1 over 10W random restriction to a size S DNF, with W DNF or CNF, the probability that restricted function's decision tree complexity is at least log 2 over epsilon is at most epsilon. Well, it just follows immediately from host-side switching lemma. D equals 2, so delta equals 1 over 10W. I mean, the switching lemma just directly says K taken to be log 2 over epsilon, that probability that the decision tree complexity of F's restricted version is at least log 2 over epsilon is at most half to the log 2 over epsilon, which is epsilon over 2. It's at most epsilon. OK, so the D equals 2 case is done. So now let's draw a picture of a constant depth circuit where D is bigger than 2. OK, so at the bottom you have the literals. And then it doesn't matter really if the next layer is and or. Let's pretend it's and. So you got a bunch of ands. And then the next layer you have ors. OK, so actually you have like DNS at this layer. These are all DNS. But you're not done. You have like, I don't know, ands up here. They feed into some DNFs. Maybe there's another or up here. I'm running out of space, but you know. Great. OK, so we're doing this like tremendous random restriction and hoping that this gigantic circuit collapses down to something like so simple it's like a constant, or it's like a constant depth decision tree. And the key idea is that random restrictions kind of compose. I'll say what I mean by that. So we're doing a random restriction where the probability that a variable is left unset is this delta. I claim that we can do it in like a multi-stage process. The choice of this final delta random restriction is like this. First do a, well, I'm not going to write first again. Do a 1 over 10w random restriction. Okay, so you go through each coordinate, set it to be true, or set it to be unset with this probability. Otherwise, fix it to plus or minus 1 randomly. Then continue by like doing a bunch more random restrictions with this parameter. So I'm actually going to say do d minus 3 more 1 over 10L random restrictions. And then let's close by doing one more. You'll eventually see why I broke it up this way. I claim that this is the same as doing this one random restriction with this parameter delta. And the reason is, like, what happens if you do like all of these steps? You go through each coordinate with probably 1 over 10w, you leave it free. And then you fix the rest to be plus or minus 1. Now, when you do another random restriction, it's like you're just going over the free coordinates. They're the only unset ones. And you set each one of those to still be free with this probability, 1 over 10L. And the rest are plus or minus 1. And so you could do that again and again and again. And at the end of the day, the probability that a coordinate is free at the very end is just like the product of all of these probabilities. Everything is independent. Okay, so this is exactly cooked up so that the product is delta. And every coordinate that's not free, whenever it happened to get set, it was 50-50 plus or minus 1. So this is exactly what we want it to be. OK, so now that we have this on the board, let me write this out here. Our goal is the probability that the decision tree complexity of the restricted function is bigger than something like log 1 over epsilon is at most epsilon. OK, so we can analyze things by kind of looking at what happens in each of these steps one by one. And basically, we're going to argue that after the first step, the first sort of random restriction, all these DNFs at the sort of bottom of the circuit become very simple. And that's going to collapse the circuit sort of by one layer. And then in the next step, we're going to show that sort of the DNFs or CNFs that are at the new bottom of the circuit collapse with high probability. We'll do a union bound. We'll try to show that after you do all of these things, this thing collapses so much so that it's like it's practically a trivial function, a very shallow decision tree. OK, so as I said, if you look at this is layer 2 of your given circuit, each of the gates at like layer 2 is like computing a DNF, or maybe a CNF, but whatever. And we can just apply the switching lemma. So after sort of the first random restriction, for each DNF at layer 2, one thing I have to sort of decide is what's my goal decision tree depth. And it's going to be L. So except with probability at most 2 to the minus L, it becomes computable by a depth L decision tree. So why is that? Well, our initial hypothesis is that the width of this circuit is at most W, which means, if you recall the definition of width, all of the fan-ins down here at layer 1 are at most W. OK, so all the fan-ins of these DNFs at layer 2 have width at most W. our first random restriction has its like delta to be like 1 over 10w. So 5 over 10w times w is a half. So this probability is always like 2 to the minus whatever. Okay, so except the probability at most 2 to the minus L, all of, well, each given DNF becomes expressible as a depth L decision tree. And if you remember an exercise I asked you to do a little while ago, DNFs and CNFs are more powerful than decision trees. In particular, anything computable by a depth L decision tree is also computable by a width L, CNF or DNF, your choice. So let's choose CNF. Okay, so assuming nothing terrible happens, and we'll count out the probability in a second, all of these DNFs can now be computed by width L CNFs. Okay, and that's actually where the name switch in the switching lemma comes from. You've somehow switched each of these things to be a CNF. And this width now is at most L. And all of these DNFs at layer 2 are now computable by CNFs. Okay, so let's do the calculation here. It works as desired for all DNFs at layer 2, except with probability at most 2 to the minus L times, I'll call it S2, where this is defined to be the number of gates at layer 2. Okay, I just union bounded over all those things. And now here's the idea of like the compression of the depth of the circuit coming in. Now we have like 2 consecutive layers of ands, so they can be collapsed into one. Like the and of an and is just an and. So anything that's going up to this and can just go directly in here, and anything that's going up to this and can go directly in. You can just cross out this layer. Okay, so the new circuit has depth d minus 1. And the number of nodes at the like new layer 2 is just at most like these are the things that are at the new layer 2. So like the number of nodes at the old or original layer 3. Okay, which we might call S3. Okay, let's say in the original circuit you had S1 nodes at layer 1, S2 nodes at layer 2, S3 nodes at layer 3, up to, I don't know, SD nodes. SD is 1 at the top. Okay, so now I think you'll probably get the gist of where this is going. Our depth has gone from d down to d minus 1, except with this probability. So now we're going to use switching lemma again. In this new circuit, okay, now we have like CNFs at the bottom and andivores, but that's okay. The new thing has width L, unless something went wrong. So now we're going to do the switching, the next random restriction with parameter like 1 over 10L. Okay, so it's exactly cooked up so that for this new layer, you know, 1 times 1 over 10L times L is like a half. So we're always going to make this thing a half. Okay, and at the new layer, we're also going to set K to be L. So let me erase this. Well, yeah. Right, so by the switching lemma again, any, you know, CNF at the like new layer 2 after the next 1 over 10L random restriction becomes computable by a width, sorry, a depth L decision tree, like I'm taking K to be L again, except with probability at most 2 to the minus L. Okay. In particular, now I can like take this to be a width L DNF. Okay, so I'm going to like switch this thing. With high probability under the random restriction, this whole thing becomes computable by a DNF. That's like an OR of ANDs. Again, with width L. Okay, so all are switchable, except with probability at most the number of nodes in the new layer 2, which is like the number of nodes in the original layer 3. So this is like at most 2 to the minus L times S3. Okay? And I'm going to keep doing this again and again, this argument again and again, d minus 3 more times. I'm going to leave like 1 off at the end. Okay, so after 2, so after 2, I do this like d minus 3 more times. D minus 3 is such that like the final thing I'm at after 2 hopefully has depth 2. Okay? Probability that the restricted function is not a width L depth 2 circuit is at most just the sum up of all of these things. S2 times 2 to the minus L plus S3 times 2 to the minus L plus dot 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 plus S, I think d minus 1 times 2 to the minus L. Okay, so I'm always getting 2 to the minus L. And I get the sum of all of the sizes of the layers, so that's at most S. Okay, and L is probably no longer up here, but if you recall, L was log 2s over epsilon. So this is epsilon over 2s times s, so that's epsilon over 2. Okay, so almost done. We've done almost all of our random restrictions, and except with probability epsilon over 2, the final thing is a width L depth 2 circuit. And now we're doing like one more random restriction with parameter 1 over 10L, so just cooked up again so that that's a half. It's just that the last step will choose K to be this log 2 over epsilon. Okay, so in the final step, this is our delta, and our K is log 2 over epsilon, so the probability that the final thing needs dt depth at most log 2 over epsilon is at most this epsilon over 2 plus the epsilon over 2 for our very last switch. That's it. Okay, so there's some bookkeeping, but the idea is hopefully not too bad. Any questions? Yeah.
So is there much known about random restrictions and other classes?
No, not really. It comes up somewhat instead in proof complexity, where you're studying for certain propositional tautologies, like what is the complexity, how big of proofs do they need in proof systems like resolution or other proof systems. And you often see like lower bounds in that form, like, oh, to prove the pigeonhole principle using a resolution proof needs exponential size. And the proof actually goes by like taking the proof and like doing random restrictions on the propositional variables in it. So the other big place I see this use of random restrictions and switching lemma is not for other circuit classes, but for proof complexity arguments. OK, so that's all we're going to do for a while about grungy circuit complexity. And next time we're going to talk about the great function majority and linear threshold functions and the central limit theorem and some other probabilistic topics.